Hello. In this video I introduce a little Python program that I wrote several years ago. And then I was studying Python, and many years have passed, and I looked back at those programs, and I found out that I was very dedicated to this task. And now let's take a look at this program. I call it prep, and this is a little 3D program that uses datatypes, and let's run this one. And here I just use the second monitor. That's why I just relocate my menus and everything here this way. And I have also coordinates tabs here. And what this program can do is, I should say, this datatypes user interface is very advanced, because those numeric fields can be used in several ways to change those values depending on the cursor position. I can scroll here those values, but let's take a look what this program can do. Load object file, and I just load in geometry file here. And here I can select an item, and I can change its position, probably. Z-axis is there via scrolling here. And I can rotate this one. And everything we can see here is datatypes, and those polygons are also datatypes draws the canvas, and everybody can say that this is slow, and of course it is. And when I just change the view and execute the rendering command, then we can see how it starts to draw out those pixels here, but it is very slow in Python. It is raw Python and only CPU based. And but my purpose with this program was to make myself familiar with all those rendering engine concepts, vertices, polygons, and how they could be drawn in 3D. Of course, they are finally they are triangles, but I don't remember what was my inner computations here. We can see that this single frame comes at a very slow pace here. And it also has some texture to it. And what I wanted to say, that I have all those programs ready, but they are not really useful in the sense that really they should be faster, all the program. And that's why I started learning this Cuda kernel programming. My dream is to make a client area or client window that uses not OpenGL or any other drawing system, but I plan to create this analogous system of myself, and this is my purpose with this Cuda kerneling. And when I started to revisit those Python concepts, in meanwhile I made programs in C programming language, and this was the TRIPS code project. But in C programming language, everything is straightforward, and you just make structures and include structure types into other structures, and this way you just expand. And when you declare that Python has some functions, sort of function arguments that are independent, then C programming language has also the same thing, but just to know about it, the function pointers. So Python, in essence, doesn't add anything to this efficiency paradigm. But anyway, Python is useful. It is a different approach, and as they say, it could be fun. And that's why I plan for the next project advance those concepts here, and use now this Cuda kerneling, and this makes this one single frame appear very fast by the idea. But as I started to reviving those Python concepts and how to program in Python, because when you program 4 years in C language, then you just want to remember what you learned all about this Python, then you have forgotten everything. And I just wanted to revive my knowledge in what I have learned in Python, and I discovered that I have learned a lot, but I have forgotten everything. And when I started to revive those concepts and learn them, then I started thinking how to create this new type of Cuda kernel program. I just closed this one up, and I open my Cuda project. This one is this new type of Cuda code, and I was stuck with a problem at how to I transfer this old knowledge to this new Cuda paradigm. And I think very many people could have this the same problem, how to solve it, because somehow Cuda concepts, everybody who has a little bit explored it, are very different from Pythonic thinking, because you don't have the privileges to submit any classes or complex data structures into Cuda kernels. You just can submit NumPy type arrays that are just essentially data types in a row, and those data types are predefined. the most lengthy data type is the complex floating point, which involves 128 bytes, really bits or bits. And we could fit into this data type some little bit of data there, structures there. But another way is to go, you disassemble those structures and complex data types into separate arrays. And this is a tedious work, and in this point you lose all the object-orientedness or everything you think Python is a favor. You just lose everything, and also everything that C offers. You just disassemble every data structure there that you have created in your Pythonic mind or smartest programming knowledge. You need to disassemble it into separate arrays that you submit and to the Cuda kernel. And that's the hardest point of it. And how to make then this program, how to breach those two thinking paradigms. On the other side, you have these objects in your CPU side, and on the other side, from the GPU side, you got those really tasks. The real thing happens there. And I thought of it that the real right way to approach this problem is to be aware of those objects that or data structures that you create in your traditional program, but to start really from other end, not to plan all those objects and everything like this. This is not the right way to do it. The right way to do it is to start from GPU side, and you really make those kernel functions that are the task heavy real duties. For instance, if I have my main purpose is to draw a frame, then I make a kernel function draw a frame. And the frame rate is up to my programming skills, but the task is to draw a frame. And what goes into a frame? Then we count up what goes into a frame. We draw triangles there, and we maybe draw polygons there, and maybe we draw lines there, and etc. And then we make the assumption of the amount of those different type of objects that we draw. And let's say we got 100 polygons and 100 lines, and then we may make a data buffer and submit this data to the GPU. And how many real amount to draw it, we could draw only 10 polygons or 10 triangles. And as we fill up it, then we make an detect and expand. Then we enlarge those buffers for the tasks. And we create those inside kernel functions that just are named draw lines or draw triangles. And as we develop our program and make it more complex, then we just enlarge those arguments or those arrays that we submit to the kernels. For instance, if we deal in the first phase only with triangles, then we make a triangle array, submit it to the device, and draw and transform them on the device. But as we wish to develop our program, maybe I wish to make an on-device subdivision there. Then I submit polygons to the device and create those triangles from those polygons, or subdivided subdivisions, and from subdivisions the triangles. And finally the triangles are drawn. And such things. My main point is that I wish to share is that first we need to deal with the end result part of it, and then we figure out what the type of structures and objects from in our traditional program support those tasks. This is the right way to approach. And I just showcase what this program also does. And I can submit the display, and we should see only this random noise here, and the mouse cursor position.